Welcome back to the deep dive. We are doing something a little different today. Usually we take a really broad concept, we try to whittle it down. Today we're starting at the other end. We're starting with a very specific, very visceral moment of panic that I think anyone in platform engineering or DevOps has felt at some point. It is the Monday morning nightmare.
It's a whole genre of horror story, isn't it?
Yeah.
Doesn't need any supernatural elements to be completely terrifying. Just an email client.
Exactly. So just to set the scene for everyone, you walk into the office, maybe you're still shaking off the weekend, you've got your coffee in hand, you open your laptop, and there it is, the email with the high importance red exclamation mark, subject line, urgent, Kubernetes node compliance requirements. And of course, it's from the security team.
Yeah, that is never a, hey, saw a cool article you might like email. That is always a, we ran an audit and you failed email.
It's the big one. It's the result of a deep audit. And the findings, they're brutal. We aren't talking about one or two minor warnings here. We're talking about a systemic failure of the cluster's entire security posture. Let's actually, let's look at the list of demands in this email because it effectively frames our entire discussion today.
Okay, lay it on me. I'm ready.
All right, finding number 1, AMI compliance. The report says our nodes are running outdated, unverified images. Some of them are like 6 months old. We're talking unpatched kernels, old versions of system. They're just sitting ducks.
Right, and that's the foundation of everything, isn't it? If the kernel itself is vulnerable, your containers can't save you. The whole house is built on sand.
Exactly. Then there's the second finding, network isolation. They found worker nodes sitting in public subnets.
Oof, that's a big one. That's the cardinal sin of cloud infrastructure. You never, ever want your worker nodes to have public IP addresses if you could possibly avoid it. That's basically just inviting the entire internet to, port scan your kubelets.
We will get to port scanning in a second because finding number 3 is security groups. Apparently, they're using the default AWS security group, which is currently configured to be, well, let's just say it's friendly. It's way, way too permissive.
We allow all traffic from other members of the same security group approach. Great for getting things working during a late-night debug session. Terrible for keeping your job.
Yep. Finding number 4, encryption. The EBS volumes attached to these nodes completely unencrypted, just plain text data resting on the disk.
So a lost snapshot or a decommissioned drive is a potential data breach. Not good.
And then there's finding number 5, the one that sounds the most technical but might actually be the most dangerous. IMDSV1 is enabled?
The instance metadata service, version 1. Yeah, that opens up a massive surface area for server-side request forgery attacks. That is a full house of compliance violations. That's not just a bad day, it's a bad quarter.
It is. It really is. And the mission, because let's be honest, you don't really have a choice here, is to fix every single one of these issues. But, and this is the constraint that makes you really start to sweat, you cannot disrupt the running workloads. You have to swap out the engine of the plane while it's flying at 30,000 feet.
And that's usually where the real panic sets in. You start thinking about spreadsheets, manual coordinating, draining nodes one by one. You're picturing yourself waking up at 3:00 a.m. to do maintenance windows for the next 2 weeks.
Usually. But today we're going to talk about why you don't need to panic. We're looking at this entire problem through the lens of Karpenter. Specifically, we're going to explore how a single configuration resource, the EC2NodeClass, can solve every single one of these problems.
And honestly, this is where Karpenter really differentiates itself from something like the legacy cluster autoscaler. It's not just about speed. It treats security as a first-class declarative configuration, not just a side effect of launching an auto-scaling group you configured somewhere else.
Okay, so before we start digging into YAML files, let's orient everyone. Most people who've heard of Karpenter know it as that fast autoscaler. But give us the 30-second architect's view. How does it actually work under the hood?
Sure. So at its core, Karpenter is an open-source node lifecycle management system. The key thing to understand is that it completely bypasses traditional AWS auto-scaling groups. It sits inside your cluster and runs this constant core loop. Watch, evaluate, provision, and disrupt.
Okay, watch, evaluate, provision, disrupt.
It watches for unschedulable pods, pods that are stuck in that pending state because there's no room for them. It then evaluates what those pods need. How much RAM, how much CPU, do they need GPUs, any specific labels or taints. Then, and this is the magic part, it provisions a node that matches those needs exactly by talking directly to the EC2 API. And finally, when that node is underutilized or empty, or as we'll see, has drifted from its configuration, it disrupts it to save money or improve security.
It's that direct provisioning part that we're really focusing on today. Because the security audit isn't complaining about how many nodes we have, it's complaining about what those nodes are made of.
Precisely. And this leads us to the most fundamental architectural decision in Karpenter, which is what they call the two-resource model. If you don't get this separation, you'll never really understand how to configure it properly, especially for security.
Okay, let's break this down then. We have two custom resources, the NodePool and the EC2NodeClass.
Right. Think of this as a very deliberate separation of concerns. The NodePool is the what.
Yeah.
It defines the scheduling constraints that your developers or that the Kubernetes scheduler itself cares about.
So things like, I need at least 4 CPUs, or I need a spot instance to save money, or this workload has to run on an ARM processor.
Exactly. Instance families, capacity types, taints, labels, startup taints, resource limits. These things are fluid. They change based on your application's needs, based on traffic, based on new deployments. The NodePool is the interface for the application developer.
Okay, so if the NodePool is the what, then the EC2NodeClass is?
The EC2NodeClass is the how. It defines the underlying infrastructure configuration, stuff developers shouldn't have to think about. Which AMI do we use? Which subnets should this launch into? What security groups should be attached? What IAM role does a node get? Is the disk encrypted? This is the interface for the platform and security teams.
I see. So it completely decouples the developer's request for some compute from the security team's mandate for compliant compute.
That's it, exactly. And the real beauty, the operational leverage, is in the one-to-many relationship. You can have 20 different node pools, one for your ANL team that needs GPUs, one for the back-end Java services, one for the front-end Node.js apps, and they can all reference the exact same single security-hardened EC2 node class.
So if I find a security hole and I need to patch the AMI, I don't have to go edit 20 different things. I just fix it in the one node class.
And it propagates to all 20 pools instantly. Well, the configuration is instant. The rollout of the fix takes time, which we'll get to later. But yes, you have a single point of control, a single source of truth for your entire fleet's security posture.
That is a massive operational win compared to managing, 20 different auto-scaling groups in Terraform and making sure they all use the right launch template.
Oh, absolutely. It's a night and day difference. In the old world, you'd have to go and update the launch template version for every single one of those ASGs. It's error-prone. Here, it's one YAML file. You check it into Git, and you're done.
Okay, the architecture makes sense. The separation is clear. So let's start attacking this audit list. Item number 1 on our nightmare email, outdated AMIs. The security team wants us off this 6-month-old image immediately.
Right. So we open up our EC2 node class manifest, and we find this section called amiSelectorTerms.
This seems straightforward enough. I just find the ID of the new patched AMI, and I put it in there. Right?
You can. That is what we can call strategy 1, the specific AMI ID. You literally put in AMI012345ABCDEF.
That feels very safe. Very explicit.
It is the most secure approach, without a doubt, because it's immutable. You know exactly what you're getting. Karpenter will never launch anything else.
Yeah.
But think about the operational overhead. Every time Amazon releases a patched EKS-optimized AMI, which is pretty frequent.
Someone has to go find that new ID and manually update the YAML file.
Correct. You need a human in the loop, or at least some external automation that's watching for new AMIs and opening pull requests.
And if I forget, or the person responsible is on vacation,
then you're insecure again within a month. You are relying on a human process to keep the version current. It's better than nothing, but it's not ideal for a fast-moving environment.
Okay, so that's the super lockdown approach. What's the alternative?
Strategy 2 is using a name pattern. The selector allows you to use wildcards. So instead of a specific ID, you could say, give me an image whose name matches Amazon X Node 1.29.
And Karpenter just, it queries the EC2 API and picks the latest one?
It finds all images that match that pattern, sorts them by their creation date, and picks the newest one.
That sounds a little dangerous.
It can be. It's a double-edged sword.
Why? Walk me through the failure mode here.
Okay, so imagine it's a Friday afternoon. You're getting ready to log off. AWS, completely unrelated to you, pushes a new version of the EKS-optimized AMI. Your amiSelectorTerms picks it up automatically because of that wildcard. A new pod needs to be scheduled. Karpenter provisions a new node. But what if that new AMI has a subtle bug in the kubelet, or a conflict with your CNI plugin, where your monitoring agent fails to start on it?
Suddenly, my entire cluster starts rolling over to a broken image while I'm at happy hour, and I have no idea why.
Exactly. That's the risk of fully automated, untested rollouts. This is why a lot of production environments avoid purely dynamic name patterns unless they have a really, really robust automated testing and validation pipeline for new AMIs.
Okay, so we have too manual on one side and too risky on the other. There has to be a middle ground.
There is. Strategy 3, using tags. This is often the sweet spot. Your CI/CD process for building images, whether it's Packer or something else, runs all your tests on a new AMI. If and only if it passes all those tests, security scans, integration tests, whatever, the pipeline's last step is to apply a specific AWS tag to it, like status approved and KHS version 1.29.
Ah, and then Karpenter isn't selecting on a name, it's selecting on the tag.
Correct. Your select would be tags that status. Now you have automation, but it's gated by your own internal validation process. You control when a new AMI is blessed production use.
That feels like the right balance of safety and automation. Now, looking at the amiSelectorTerms, I noticed something interesting in the documentation. It's a list. You can provide multiple terms.
Yes, and it evaluates them in order using a logical OR. This is really powerful for fallbacks in complex scenarios. You can say, term 1, look for an AMI with the tag status, golden release. If you don't find one that matches, term 2, fall back and look for one with the tag status approved. If that also fails. Term 3, as a last resort, look for the latest one by name pattern, Amazon X Node 1.29. It gives you a hierarchy of preferences.
Wait, I want to double-click on something you mentioned earlier about the risk of picking up the wrong image, the owner filter. That sounds important.
Ah, yes. This is a critical security control that is on by default, but is often overlooked or misunderstood. By default, Karpenter is configured to only look at AMIs owned by self, which means your own AWS account or Amazon.
Why is that restriction so important?
Let's go back to that threat model.
Yes.
Let's say you're using that dynamic name pattern strategy 2, and you're looking for something common, like Ubuntu 20.043.
Okay, seems reasonable.
Anyone in the world can publish a public AMI on the AWS Marketplace. I could go into my personal AWS account right now, build a malicious image that contains a crypto miner or a backdoor, and name it Ubuntu 20.04 Super Secure Patch Latest. If Karpenter didn't filter by owner and my malicious image happened to be newer than the official one from Canonical,
Karpenter would happily boot it up and add it to my cluster.
it would. You'd be running my malicious code inside your private network that is a supply chain attack on your infrastructure. It's a honeypot. So that owner filter is your absolute safety net. It ensures you are only pulling from trusted sources that you've explicitly defined.
Wow. Okay, that's a huge deal. So for our audit, we'll use the tag strategy and rely on that owner filter. Finding number 1, resolved.
Check. Moving on.
Finding number 2, network isolation. Nodes in public subnets. This seems like it should be a simple fix, but my gut tells me there are dragons here.
There are. It's easy to get the basics right and the edge case is wrong. The fix, as you'd expect, is to use the subnetSelectorTerms field in the NodeClass.
So same as with AMIs, do we just paste in the subnet IDs? You know, subnet ABC1234, subnet diff5678.
You can, but please, please don't. That is instant technical debt. It's brittle. What happens if you redeploy your VPC using Terraform? Those IDs will change. What if you want to reuse this NodeClass in a different region or for a different cluster? Those IDs are completely useless.
So it's tags again. Of course.
It's always tags. The established convention here is called the discovery convention. You go into your VPC and you tag all your private subnets with a special tag, carpenter.dishdiscovery.my-cluster-name. You might also add another tag like tier.private. Then, in the EC2NodeClass, you just tell Karpenter to find subnets that have both of those tags.
I see. That makes it dynamic. If I add a new private subnet in a new availability zone, I just tag it correctly, and Karpenter will automatically start using it without me touching the NodeClass.
That's the power of it. But here's where it gets interesting. How does Karpenter actually pick a subnet from the list of valid tagged options?
Good question. I assume it just picks one at random.
It's much smarter than that. It uses a multi-factor decision process.
Right.
First, it filters by the tags you specified. Then, it considers the pod's own scheduling constraints. If a pod needs to run in, say, availability zone USEast 1A, Karpenter will only look at your tagged private subnets in that specific AZ. Then, and this is the really clever part, it looks at IP availability.
What do you mean?
Let's say you have 2 valid private subnets in USEast 1A. One has 100 free IP addresses, and the other has only 5. Karpenter will query the EC2 API, see those numbers, and it will always prefer the subnet with more available IPs to avoid causing subnet exhaustion.
That's brilliant. So it's actively trying to prevent future problems. But what about that scenario? What if the pod has to run in Zone A, but the private subnet in Zone A is completely out of IPs? It's full.
That is a classic subnet exhaustion scenario and a very common cause of production outages.
What does Karpenter do? Does it crash? Does it panic and throw the node in a public subnet just to satisfy the request?
This is where Karpenter's safety features really shine. It will not launch a node. The pod will stay pending.
That sounds bad for the application owner. Their pod isn't running.
It's operationally annoying, yes, but it is securely correct. The alternative is what's called failing open, launching the node in a public subnet just to get it running. That would be a direct violation of the security policy we're trying to enforce. Karpenter respects the constraints you put in subnetSelectorTerms, absolutely. It will fail safely or fail closed rather than violate your rules. It forces you to go and fix the underlying problem, which is your lack of IP space.
Okay, that's incredibly reassuring. It won't try to be helpful in a way that gets me fired.
Precisely.
So we've locked the nodes into private subnets using discovery tags. Finding number 2 on the audit, resolved.
Check.
Now for finding number 3, the firewall. The security groups, the audit says permissive default, which is a polite way of saying wide open.
Right, which usually means it's using the default VPC security group that allows all traffic from any other resource in that same group. It's essentially a flat network.
So we need to create a new, much stricter one. We'll use securityGroupSelectorTerms, again, selecting by tags, I assume. But I want to get into the weeds here. What are the exact firewall rules a Kubernetes node needs? Because I feel like people just copy-paste allow all because they're scared of breaking things they don't understand.
That's exactly how you fail audits. You need to apply the principle of least privilege. There are really only a few critical things a node needs to function.
Okay, list them out for us.
First, inbound on TCP port 10250, but only from the EKS control plane security group.
That's the kubelet API port, right?
It is. This is how the Kubernetes control plane talks to the worker node. It's how it says, launch this pod, give me the logs for that container, exec into this container for debugging.
Let's pause right there. Exec into this container. So if I'm an attacker and I can get onto your network and I can talk to port 10250 on one of your nodes.
You can effectively run commands as root inside any container on that node without needing to go through the Kubernetes API server's authentication. It is game over. That is why that port must only accept traffic from the control plane security group, not from the internet, not from your office VPN, not from other worker nodes, just the control plane.
That is a war story waiting to happen. Okay, what else is on the list?
You need to allow inbound traffic from other worker nodes on the ephemeral port range, which is usually 1025.65335. This is for pod-to-pod communication when you're using services with node port.
Got it. And what about outbound? What does the node need to talk to?
The big one is outbound on TCP port 443 to everywhere. The node needs to talk to a lot of AWS APIs. It needs to talk to ECR to pull container images, S3 for logs if you're using a sidecar, and most importantly, the EKS API server itself. If you block 443 outbound, the node is a brick. It boots up, but it can't download its configuration or join the cluster.
In DNS, I assume?
Of course. Outbound on port 53, both UDP and TCP, to your VPC's DNS resolver. If it can't resolve ec2.useast-1.amazonos.com, it can't make any of those critical API calls.
Okay, so we build a security group with just those specific roles. We tag it with something like Karpenter Node Profile, JustLine, then we tell the EC2NodeClass to use it.
Exactly. And just be aware, Karpenter allows you to specify multiple selector terms here. It will find all matching security groups and attach them all, but there's an AWS limit. You can only attach, I think it's 5 security groups to a single network interface. So if your selectors match 6 or more groups, the EC2 launch will fail.
Good catch, so keep it consolidated. Okay, finding number 3, resolved. Now let's talk about data. Finding number 4, unencrypted EBS volumes.
So this one is very easy to fix in the configuration, but it has some nuance in the implementation that can trip people up. We go to the blockDeviceMappings section in the EC2NodeClass.
And we just said encrypted.
True.
That turns on encryption, yes. But the audit usually requires more than that. They'll want encryption with a customer-managed key, a CMK from KMS. Why isn't the default AWS managed key enough? It's still encrypted, right?
It is, but it's about control and governance. With a CMK, you control the key policy. You can define exactly which IMM roles or users can use the key. You can audit every single use of that key in CloudTrail. You can enable automatic key rotation. And critically, if you suspect a breach, you can disable or delete the key, effectively rendering all the data on those volumes unreadable. You have the kill switch.
Okay, that makes sense. So we go into KMS, create a new key, and we paste its ID or ARN into the common keyed field in the node class.
And here's the trap that I have seen so many people fall into. You do that, you apply the change, Karpenter tries to launch a new node, and it fails with a cryptic authorization error.
Why? What do we miss?
Permissions. It's always permissions. There are two sets of permissions you need. First, the IAM role that the Karpenter controller itself is using needs permission to common nodes, create, grant, and calendars generate data key on that specific key. Second, the node's IAM role, the one the kubelet runs as, needs permission to columns.decrypt.
So it's not enough to just reference the key. The key's own policy has to be updated to trust both the Karpenter controller role and the node instance profile role.
Exactly. I have personally seen engineers spend days debugging EC2 launch failed errors because the KMS key policy was too restrictive. It's the first place you should look.
Okay, great tip. Now, while we're talking about storage, the audit didn't mention performance, but I noticed our current nodes are using GP2 volumes.
Oh, legacy storage, a classic.
The source material we looked at strongly recommends GP3. Break down the math for us. Why is the switch so important?
It's all about decoupling performance from size and avoiding the burst balance cliff. With GP2, your IOPS, your input-output operations per second, basically how fast you can read and write, are directly tied to the disk size.
Yeah.
You get a paltry 3 IOPS per gigabyte.
So if I have a small, say, 50 GDB boot drive,
You get 150 baseline IOPS. That is nothing. Now, GP2 has this concept of burst credits. You accumulate them when you're idle, you spend them when you're busy. But what happens when a node starts up? It tries to pull a large container image. That's a huge read operation. You burn through your entire burst balance in seconds. Once those credits are gone, the disk throttles down to that pathetic 150 IOPS baseline. Your node becomes incredibly slow, almost unresponsive.
so it looks like the node has crashed, but really it's just I/O starved. It's waiting on the disk.
Exactly. It's a very common cause of nodes failing to join the cluster in time. Now, GP3 completely changes this model. You can have that same 50 GB drive, but you get a guaranteed baseline of 3,000 IOPS, 20 times better regardless of the size. And you can provision even more if you need it. Plus, it's usually about 20% cheaper per gigabyte.
Wait, so it's significantly faster, it's cheaper, and it doesn't have that burst balance cliff that can make your nodes fall over.
There is literally no reason to use GP2 for new deployments in 2026. GP3 is superior in every way for almost every workload.
Done. We are upgrading to GP3, maybe 100 GB size to be safe, encrypted with our new CMK. Finding number 4, resolved.
Now we get to the final boss of the audit, finding number 5. IMDSv1 enabled.
This was the instance metadata finding. I think we need to explain this one carefully because it's a bit abstract and a lot of people just glaze over it.
Okay, so every EC2 instance under the hood has a special local web server running at a magic IP address, 169.254.169.254. If you curl this address from the instance, it gives you metadata about itself. What is my public IP? What availability zone am I in? What is my instance ID?
And crucially, what are my IAM credentials?
Right. If the node has an IML role attached to it, this endpoint will serve up the temporary AWS access key, secret key, and session token for that role.
So the problem with version 1, IMDSv1, is that it's just a simple, unauthenticated JTT request?
Exactly. Curled http.169.254.169.24 fabric lit as metadata security credentials, my node role. No special auth, no headers, just give me the keys.
And this leads to the vulnerability known as SSRF server-side request forgery.
Right. So imagine you have a vulnerable web application running in a pod on that node. Maybe it's a proxy or an image processor that can fetch images from a URL or a PDF generator. If an attacker can trick that application into making a web request on their behalf, they can tell it to fetch that magic metadata URL.
The application running inside the instance makes the request, and the metadata service happily hands over the credentials. The attacker gets the keys.
And since those keys belong to the node's IAM role, the attacker can now do whatever the node can do. If the node can pull from ECR, so can the attacker. If the node can write to an S3 bucket, so can the attacker.
So the fix is IMDSv2. How does that change things?
IMDSv2 adds a layer of protection. It requires a session token. Before you can get any metadata, you first have to do a PUT request to a specific URL to get a short-lived token. Then you have to include that token in the header of your subsequent KDT requests. Most simple SSRF exploits can't forge a PUT request with specific custom headers. It just breaks the attack chain.
Okay, so in our EC2NodeClass, we go to the metadata options block and we set HTTP tokens required.
That's the switch that enforces V2 and disables V1. But you're not done. Here's the critique we need to address deeply. There's another field called HTTP put response hop limit.
And the default for that is often 1.
It is. And if you leave it at 1 in a Kubernetes environment, you're going to have a very bad time. Your applications will start mysteriously failing.
Why? What does hop limit even mean here?
It's basically the TTL, or time to live, of the network packet. It comes down to how Linux network namespaces work. Think about the packet flow. Your application is running inside a container, which has its own isolated network namespace. You run the AWS DK, it tries to get credentials. The packet leaves the container's network namespace, that is hop 1. It crosses the virtual Ethernet pair, the VEF device, to the host's main network namespace.
All right.
Then it needs to travel from the host's namespace to the actual metadata service endpoint. If the hop limit is 1, the packet's TTL expires as soon as it hits the host namespace. It gets dropped. It never reaches the metadata service. From the container's perspective, the request just times out.
So any pod that uses an AWS SDK and app trying to write to DynamoDB or read from SQS will fail because it can't get its credentials from the metadata service.
Exactly. So for Kubernetes, you must set the hop limit to 2. 1 hop out of the container into the host, and a second hop from the host to the service.
Got it. That is a subtle but critical detail. So HTTP tokens required and HTTP put response hop limit 2.
But wait, while we're here, there's a much, much better way to handle credentials entirely. We've been talking about the node role having permissions. In an ideal world, the node role should have almost 0 permissions beyond what it needs to pull images and join the cluster.
But my application needs to talk to S3. How does it get permission?
I use IRSA. IAM roles for service accounts. This is the modern best practice.
Okay, explain how that works under the hood, because it sounds like magic.
It's clever. It uses OIDC OpenID Connect. When you enable it on your EKS cluster, the cluster itself acts as an OIDC identity provider. It can issue signed tokens. When a pod starts that is linked to a specific Kubernetes service account, a special mutating webhook automatically injects a signed token file, a JWT, into the container at a well-known path.
A JSON web token.
Yes. The AWS SDK in your application is smart enough to find this token. It takes the token and sends it to the AWS Security Token Service, STS, and basically says, hey, AWS, here is a token signed by my EKS cluster. It proves that I am the MyApp service account in the default namespace. Please trade this token for some temporary AWS credentials.
And AWS, because you've set up a trust relationship, validates the signature on the token and hands back the keys.
Exactly. And the beauty of this is that the node never sees those S3 permissions. The credentials are scoped only to that specific pod. So even if an attacker breaks out of a container and manages to hit the node's metadata service, all they get are the credentials for that bare minimum node role, which shouldn't have access to any of your sensitive data. It's the ultimate defense in depth.
That is the ultimate application of least privilege.
Fantastic. So, to recap the fix for this finding, enforce IMDS v2, set the hop limit to 2 as a fallback, but the real goal is to move all applications to use IRSA so the node role is neutered.
That's the path to enlightenment.
Okay. Finding number 5. Resolved. We've done it. We've gone through the whole list.
Right.
We have a compliant EC2NodeClass configuration.
But we aren't done. We've just written the YAML. The blueprint is there. Now we have to talk about day 2 operations and advanced customization.
Right. The user data block.
Yes. Sometimes the declarative config in the NodeClass isn't enough. You have a compliance requirement to install a special security agent or a logging daemon, or you need to tweak a kernel parameter via sysdel. This is where user data comes in. You can provide a script that runs when the node boots. But I have heard this is a nightmare to format correctly.
It can be. It's because you can't just provide your own script. Karpenter also has its own critical bootstrap script that needs to run to configure the kubelet and join the cluster. So you can't just overwrite the user data. You have to merge your script with Karpenter's. The way you do this is with a standard called MIME multi-part formatting.
Oh, God. That sounds like building an email by hand from the 1990s.
That's basically what it is. You have to construct this complex base64 encoded string that says, here's my shell script as one part, and here's Karpenter's bootstrap data as another part. It's very easy to get wrong.
And what if you're using something like BottleRocket, which we mentioned earlier?
It gets even more complicated. BottleRocket doesn't use shell scripts for configuration. It uses a TOML configuration format. So your user data has to be a TOML snippet, which is then wrapped inside a NOMI part, which is then base64 encoded.
This sounds like something I am definitely going to mess up the first 5 times.
You will. Everyone does. The key is to test it carefully, but it is incredibly powerful when you get it right. For example, We mentioned pre-pulling images earlier to speed up pod startup.
Right, for big data science models or something.
This is how you do it. In your user data shell script, you can just run CTOR images, pull my huge dash model.latest. By the time the node boots, joins the cluster, and reports ready to Kubernetes, that multi-gigabyte image is already on the local disk. When your pod gets scheduled there, it starts in seconds instead of minutes. It's a huge performance win.
That is a pro tip. Okay, last major topic before we wrap. We've applied this beautiful, secure EC2NodeClass. The cluster is compliant. But next week, a new CVE drops, a new patched AMI comes out, or we decide to change the security group rules.
The dreaded update cycle. Day 2.
How does Karpenter handle this? Because with the old cluster autoscaler, this was a manual, painful process. We had to go in and terminate old nodes by hand to force them to refresh from the new launch template.
This is one of Karpenter's killer features, built-in drift detection.
Define drift in this context for us.
Okay, so Karpenter calculates a hash of your EC2NodeClass configuration. All of those things we just said. The AMI selectors, subnets, security groups, everything. Let's say the hash of our new secure configuration is ABC. When it launches a node, it tags that EC2 instance with Karpenter-NodeClass hash ABC.
Okay, so it knows what it was built from.
Right. Now you come along next week and you edit the YAML. You change the AMI ID to the new patched version. The content of the EC2NodeClass is changed, so its hash changes. The new hash is XYZ. Karpenter periodically scans all the nodes it manages. It sees a running node with the tag ABC, but it knows the desired state is now XYZ. The node is out of date. It marks that node as drifted.
Does it just kill all the drifted nodes at once?
No. That would be a mass extinction event and would cause a huge outage. It's much more graceful. It respects the disruption budget you configure in the NodePool.
Explain that budget.
You can configure a budget that puts constraints on how aggressively Karpenter can disrupt nodes. You can say, only disrupt 10% of the cluster at a time, or only 5 nodes at once, or don't disrupt anything between 9 a.m. and 5 p.m. on weekdays. When it decides to act on a drifted node, it follows a safe, rolling replacement process. It will provision a brand new replacement node with a new XYZ config, wait for it to be fully ready and joined to the cluster, then gracefully drain the pods from the old ABC node, and only then will it terminate the old instance.
So it's a completely automated, safe, rolling replacement.
Yes, we need to distinguish that from a related concept called consolidation.
How is consolidation different from drift? They both seem to replace nodes.
They do, but for different reasons. Drift is about fixing a configuration mismatch. The node is not compliant. Consolidation is about fixing cost and utilization inefficiency.
Give me an example of consolidation.
Okay, it's late at night, traffic is low, you have one node that's only 50% full, and you have another node that's only 20% full. Karpenter's consolidation logic sees this and says, hey, if I move the few pods from the 20% full node over to the 50% full node, I can delete the now empty one and save money.
Or what if it could replace both of them with a single, cheaper instance type?
Exactly. It is constantly solving a bin packing problem. It might say, I see these two expensive C5.2x large nodes. I calculate that I can replace both of them with one cheaper M6G.4x large Graviton instance and fit all the pods. So it will provision the new node, drain the old ones, and terminate them.
So drift fixes security. Consolidation fixes cost.
Correct. And they both work together in the same graceful disruption loop, respecting the same budgets.
But wait a minute. If I change the AMI ID in the EC2NodeClass, as in our example, doesn't that technically mark every single node in the fleet as drifted?
It does, instantly.
So even with a disruption budget, I'm effectively resigning the entire fleet over the next few hours or days.
Yes. And that is a good thing. You want the entire fleet to be on the new secure AMI. But you are absolutely right. You need to be prepared for that churn. This is why your applications must have pod disruption budgets, or PDBs, set up correctly.
So the safety isn't just in Karpenter's configuration, it's in the application's Kubernetes configuration too.
Always. If you have a critical application that only has one replica, and you define a PDB for it that says min available 1, you are telling Kubernetes you can never, ever evict this pod. In that case, Karpenter will try to drain the node, the drain will get stuck waiting for that pod to move, and it will eventually time out. The drift will sit there forever, blocked by the application's refusal to be disrupted.
It gets blocked. Wow.
Exactly. Operations is a team sport. The platform team provides the mechanism for safe rollouts, but the application teams have to opt in by configuring their workloads to be resilient.
Well, we have covered a massive amount of ground today. We started with a terrifying audit report, and we turned it into a bulletproof EC2NodeClass.
We did. We lock down the OS with AMI selectors, the network with subnet selectors, the firewall with security groups, the storage with encryption, and the identity with IMDS-v2 and IRSA.
And we configured Drift to handle the day 2 operations automatically.
And hopefully help people avoid the common pitfalls, like the IMDS HOF limit and the KMS permissions errors.
To wrap this all up, I want to come back to that first idea we discussed, that separation of concerns, the two-resource model.
It's so fundamental. I think it's the future of how platform engineering should work.
Why do you say that so strongly?
Because it commoditizes the infrastructure. It creates a clean contract. Think about it. If the developer just asks for resources, CPU, memory, maybe an architecture in the NodePool, and you, the platform owner, control the EC2NodeClass.
Yeah.
You can swap the underlying hardware entirely without the developer even knowing. You can move your entire workload from Intel to ARM-based Graviton processors just by changing the AMI selector of the NodeClass and adding an architecture requirement to the NodePool. The developer doesn't have to change a single line of application code.
You could move from expensive on-demand instances to cheap spot instances with an on-demand fallback for your dev environment with a one-line change.
You could, in theory, even have an EC2 NodeClass that points to AWS Outposts hardware in your own data center. The abstraction holds. The what is completely separate from the how and where.
It truly turns the hardware into just another piece of software configuration.
Security as code. Infrastructure as a declarative state. That's what this really enables. It stops being this manual, imperative chore and becomes part of an automated, auditable pipeline.
So the next time you get that email with the red exclamation mark,
Don't panic. Just open your IDE, edit the EC2 NodeClass YAML, commit it to Git, open a pull request, and let the GitOps pipeline and Karpenter handle all the heavy lifting.
and maybe buy your security team a coffee. They are, after all, just doing their job.
Maybe. Or just send them a permalink to the Git commit and say, check the hash.
Check the hash. I love it. That's the new "it works on my machine." Thanks for tuning in to this deep dive on Karpenter and Kubernetes compliance. We'll see you on the next one.
Stay secure out there.